limit Sx approaches pi over 4 from 1 minus tangent x over sine x minus cosine x. Good, perfect. Okay, what do you think about this? Well, we don't know, we have to plug it in. What if I plug in and I get 2/3 and I'm done? So, plug it in and tell me what you get at the top. Where is the numerator going? Anyone, please?
Wouldn't it be 0?
Yes, 1 minus tangent pi over 4, which is 1. 1 minus 1 is 0. Awesome. What about the denominator? What about the denominator? Anyone, please?
Also 0?
Yes, because they are the same at pi over 4. Square root of 2 over 2 minus square root of 2 over 2 is 0. For this one, we can apply L'Hopital's rule. Let's differentiate 1. What do we get? This is the only time we differentiate like this. We never differentiate a quotient like this. But if it's a limit of a function and the initial assessment is 0 over 0, we can. This is one time we are allowed to do this. Okay, 1 prime is
0.
perfect. Negative. What about tangent prime? That is secant squared. We proved it together a few minutes ago. The denominator now, sine prime is cosine x, and cosine prime is negative sine x. Now we try again. So there is a negative. When we plug in pi over 4, remember secant squared is 1 over cosine squared. Cosine pi over 4, I'll come back to this, I need more room. So please remember, this is my page 8, okay? Sine pi over 4 equals cosine pi over 4 equals the square root of 2 over 2. So when we look at 1 over cosine squared pi over 4, then we have 1 over this squared, because cosine pi over 4 is this, but I have to square it. So it's 2 over 4. And when I flip, I get 2. 1 over 2. So 2 over 4 is 1 over 2, and I flip and I get 2. So this is secant squared pi over 4, which is 2. So then the numerator is negative 2. The denominator is the square root of 2 plus the square root of 2, which is 2 the square root of 2, which is the square root of 2. So the square root of 2 plus the square root of 2 is 2 the square root of 2, which reduces to the square root of 2. Yes, we will rationalize. These will go away, so the answer is negative the square root of 2. We had enough information and skill to use L'Hopital's rule here. Any questions? Yes?
The paper that's underneath where you like ran
Yes.
over, can you pull that down? Yeah, right there.
Okay, and we decided to look at one more, which was 60. So let's take a look at 60. And that is limit as x approaches 1 from sine x minus 1 over x squared plus x minus 2. Perfect. So can anyone tell us the initial assessment? And then I wanted to talk about one more limit when theta approaches 0 from cosine theta minus 1 over theta. But after we finish this one. Because this is another very important result. We're going to box it in. Okay. So can anyone give us the initial assessment? Please, everyone, please talk to me. Tom, I haven't heard from you if you want to say anything. I don't like calling on anyone. Just
I'm not sure.
Okay, that's okay. But I was saying just plug it in and give us the initial if you want. Or anyone else. Yes. Just the initial for now. And of course if anyone wants to help, please jump in.
Mm-hmm.
0 over 0.
Yes, of course. Of course. Perfect. So now notice that obviously there is nothing I can do here. I can immediately notice this by moving 1. So I have what I want so far. But I have to work on the denominator. Can anyone tell us anything about the denominator? Well, since we plugged in 1 and we got 0, one factor must be x minus 1. There is no other way. We would have not gotten the 0 if a factor weren't x minus 1. But we need to discover the second factor.
That would be positive 2.
But it has to have x.
Oh, x.
You mean x plus 2.
X plus 2.
Perfect, indeed. X squared minus x plus 2x minus 2. Perfect. So now, where is this going? Sine x minus 1 over x minus 1. I know there is an extra piece, but I'm only asking sine x minus 1 over x minus 1. Let's write it one more time because it's not clear. So limit Sx approaches 1 from sine x minus 1 over x minus 1, x plus 2. Or I'll put it in parentheses. Oh, that's not what I meant to say. I meant to write x minus 1 approaches 0. When x approaches 1, subtract 1 from both sides, x minus 1 approaches 0. So, where is this going? When x approaches 1 or x minus 1 approaches 0. Where is this going?
So 1.
Thank you very much. So now, if this is gone because it's 1, can anyone give us the final answer for the final limit? Where is the numerator going? Where is the numerator going? There is nothing else. Where is it going?
1.
Yes. Can anyone tell us where is this going when x approaches 1?
3.
That's it. That's the limit. Good. Let's plug it in and see what is the initial assessment. And then we can apply L'Hopital's rule. We have enough information and tools to do that. Can anyone tell us where is the numerator going?
It's approaching 0.
Yes, over 0. Perfect. So let's apply L'Hopital's rule. Can anyone differentiate the numerator?
negative sign.
Excellent. Can anyone differentiate the denominator?
1.
Excellent. Can anyone give us the final limit where we apply the limit and the limit operator disappears? We discussed this like 3 or 4 times already, right? Tonight.
Was that -1?
This is sine. It's not cosine. It's sine. When up. Sine theta when theta approaches 0.
That can be 0.
Thank you. Good. Awesome. So when sine approaches 0, when theta approaches 0, sine theta approaches 0, 0 times -1 is 0. Perfect. Awesome. Good. Well done. Thank you for your contribution so far. Section 3.4. The chain rule. This is the rule of the rules. The rule of the rules. Very important. Very, very, very important. Okay, so let's start. Okay, I'm going to write a function or several functions. Let's say the square root of x to the third plus 2. Let's say e to 4x squared. Let's say tangent of 4x. Let's say sine x squared minus 2. In all these situations, you see something called function composition. Function composition. You don't see e to the x. You don't see the square root of x. You don't see tangent x. You don't see sine x. No. You see the square root of x cubed plus 2, e raised to 4x squared, tangent applied to 4x, sine applied to a polynomial, quadratic. In all these situations, there is something called the inner function and outer function. I can have 4 or 5 different inner, outer, not just 2. Let's look at the first one. Can anyone tell us what is the inner function? What do I mean by inner function? So when I look at this, I know exactly which portion I have to perform first. If you ask me, plug in, replace x by 5. I know exactly which quantity I have to determine first and which function I have to apply second. So what is the inner function for this one? Tell me whatever you're thinking. It's okay.
3 cubed plus 2.
So you're talking about the inner function as x cubed plus 2. Good. Now after that, when I get one number, which function I apply to this number?
The square root.
The square root of x. So the inner function is this. When I'm done with it, the outer function is this. Awesome. So now let's talk about this one. Inner, outer. E raised to 4x squared. Which is the inner and which is the outer?
Inner would be 4x squared.
Good. When I'm done and I obtain one number, which function I apply to that one number?
E to the power of
Natural.
x.
That's it.
Okay.
Excellent. Next one. Inner, outer. Which is the inner function?
Would that be 4x?
Excellent. When I'm done and I get one number here, which function, original function, I apply to this number? My marker is drying out.
Tangent x.
Thank you so much. Good. Awesome. In the past, I don't remember when, which semester, I was saying my markers are dry, getting dry, and one student said they must be too cheap. So I guess they are cheap. Anyway, good. As long as I can put a smile on your face, that's fine. Inner, outer, please. My cheap markers. So
Inner is x squared minus 4.
finally, x squared minus 2. Good. And the outer? The outer would be?
Sin x.
Sine x. Okay, what's with all this? Well, when we differentiate a function composition, we have to be aware of all inner and all outer, because I can have outer, inner, innermost, and so on and so forth. Not just two. I may have multiple steps. So when I evaluate the inner and then the outer. When I differentiate using the chain rule, I differentiate the outer first and then the inner. So, all right, page 9. So let me explain. So let's say we have sine of that x squared minus 2, and I want to differentiate this. I have to start, I didn't show the formula, I just want to start with these examples. So I look at the outer, and I have to differentiate it first. So the outer prime will be cosine of the inner times the inner function prime. And of course, I will write it 2x cosine x squared minus 2, because I don't want anyone to think that this is multiplied by 2x and then apply cosine. No. 2x is in front. Let's say the square root of x cubed plus 2 prime. I'll write more formulas in a minute and I'll explain again. So when I differentiate the square root, what do I get? Forget about the inner for a moment. We differentiate the square root. What do we have to write?
You get 1 over 2 square root.
Very good. Of x cubed plus 3, plus 2, times the inner function prime. Can anyone differentiate this? And I'll write it here.
3x to the power of 2.
That's it. So now we condense by writing 3x squared over 2 the square root of x to the third plus 2. So let me write here for a moment. We know that the square root of x prime is 1 over 2 the square root of x. And to be exact, I should have said times the inner function prime. But why didn't I? Why didn't I say times the inner function prime for plain x?
Because it's just 1.
Exactly. Perfect. But now if I have a function, then it's a different story. It's 2 over the square root of the function, but times the function prime. Exactly what we wrote here. So this is the rule for the square root of a function, prime. This, they are identical, but we didn't write this because it was 1. But here it's not 1. This is not 1. It's 3x squared. So I always have to say times the inner function prime. Always. If it is 1, then you don't have to. But if it's not 1, then you have to. Always say times the inner function prime. Okay. So also let's look at the tangent and also e to 4x squared. So now, okay,